All right, this is the first midterm from the fall 2022 semester of CS 251. This is actually the exact midterm that I took about a year and a half ago now, so I actually kind of remember some of these. So hopefully this goes pretty smoothly. Let's start with question one is, don't tear your page off or cheat or anything. Question two is an actual question, so let's start with this one. Amy developed an algorithm and ran several experiments on it to analyze its runtime. She collected the following data. So it looks like we have, in each of these, we have an input size n and an output runtime of t of n. So for example, if you put an input size of 80 into this function, it's going to take about 60 seconds, or however long the units are, it doesn't really matter. All right, so knowing that, what are these questions asking? The algorithm took too long for an input size of n equals 640. Assuming we can use the power law, t of n equals an to the power of b, to propose a runtime expression of the algorithm, make a reasonable prediction for t of 640. So you'll notice that t of 640, we don't really have that in this table here. It only goes up to about 320. But if you notice how each of these are being stepped in a way, you can actually make a really accurate prediction for what future elements are going to look like. So for example, if you look at the first element compared to the second element, looks like it's doubling in size. 80 is 2 times 40. So at this step, it is doubling in size. Now, if we look at the next step, between 80 and 160, it's doing the exact same thing. It's doubling in size. So it's doing the same thing there, and it's also doing the same thing for the last step. 160 times 2 is 320. So it looks like at each step it is doubling in size. The input size is doubling. And then if we look at the output size, it looks like it's going to quadruple at each step. So 15 turns into 60, that is 4 times. 60 turns into 240, that is also 4 times. And same with 240 into 960. These are all steps of 4 times at each step. So knowing all of this, we are asked to find t of 640. So if we kind of imagine having an input size at the very end of, let's do 640 here, this is going to, it looks like it's going to double in size again. 320 times 2 is 640. So it's going to double in size. And then using that, we can kind of make a prediction on the other side for how much this is going to grow. Since we made one more step off of the last step there, this is going to be 960 times 4. So 960 times 4 I cannot do in my head, so let's do it off to the side here. 960 times 4, 0, that's 240, and 380. Awesome, 3,840. So that is a really accurate and reasonable prediction for that next step of that chart there. So we're going to write down that t of 640 equals 3,840. That is question A. So now going on to question B, assuming we can use the power law here, what is the value of B? So the value of B here is, we have a little formula for it. So whenever, so we have this B here in the power law. If we want to calculate that, this B is equal to logarithm of the base, which is going to be this leftmost step here. So let's say this is going to be, that's going to be 2. And then the value that we have on the inside of it, that's going to be the rightmost step, so the step of the output. So that is 4 times here, so we're going to write a 4 right there. And if we do that math, log base 2 of 4 is 2. So that is the value of B. So what this says here, the power law, since this exponent is 2, it is n squared, this algorithm, that Amy developed, it runs in polynomial time. It runs in n squared time, which is O of n, or O of n squared there. So that is how fast this algorithm runs, and that is the exact value of B here. Question 3. Alice, Jane, and Elizabeth designed 3 new algorithms for Mango Enterprises. Let T sub A, T sub J, and T sub E denote the worst case running time for each of their 3 algorithms on any input size of n. Mango Enterprises works with very large data sets, so they're only able to use algorithms with a worst case time complexity of quadratic time of O of n squared. So let's start with part A here. Alice runs her algorithm on data sets of size n equals 10 to the 6th power and n equals 10 to the 7th power, and finds that their algorithm terminates in 3 times 10 to the 6th power and 3 times 10 to the 7th power steps, respectively. Based on these observations, can Alice conclude that her algorithm runs in linear time, in O of n time? So when I took this exam a year and a half ago, I'm pretty sure I got this one wrong. I said that yes, you can conclude that that Alice's algorithm terminates in linear time because you just kind of look at these input sizes and their output run times and sort of infer that it's linear. So for example, if you look at this input size here of 10 to the 6th power, and you look at its output runtime, that's just 3 times 10 to the 6th power. So you kind of get the idea that, okay, maybe it's just multiplying it by 3. And that's reinforced by the second data point that you have here. For the input size of 10 to the 7th power, it is going to take 3 times 10 to the 7th power steps to complete. So now you're getting a really good idea that, okay, maybe this is going to take exactly 3n time for an input size of size n. And that's basically what I wrote down, but unfortunately you can't quite draw that conclusion. And let me explain why. So if we kind of look at question 2 for this one, we had, it looks like 4 rows of data to sort of estimate Amy's algorithm here. We had these 4 rows in that table of inputs and their runtimes, and using all 4 of those, we were able to pretty accurately determine what this power law is. We determined that it runs in quadratic time, in O of n squared time. But unfortunately, we don't have that kind of data available here. We've only got 2 sets of input sizes and their runtimes. And basically because of that, we can't really determine what this runtime is here, or at least its worst case runtime. So because of that, no, we cannot conclude that Alice's runtime is O of n. And that's basically what I wrote down here. No, because Alice's algorithm does not have enough data to go off of to determine its runtime. Part B, Bob analyzed Jane's algorithm and claims to have a proof that T sub j is big O of g of n for some function g of n such that it is greater than or equal to n to the 9th power. Assuming that Bob's proof is correct, is this a sufficient reason for Mango Enterprises to discard Jane's algorithm? So keep in mind that we want all of Mango Enterprises' algorithms to have a worst case runtime of n squared or better. So initially we kind of want to say that, yeah, maybe we should discard this because n to the 9th power is way worse than n squared, and that since Jane's algorithm is O of n to the 9th power, yeah, that sounds like it's pretty bad. But we kind of can't. And the best way that I want to explain this is kind of the way that I think about big O notation and how different algorithms can relate to each other based off what you know about their big O between them. So let's call g of n, let's make this red. And since we know that it is n to the 9th power, let's kind of draw this all on a graph. So if we kind of have, maybe I have an explanation later on, so I don't really want to write it here. Maybe we can do it off to the side. So let's do a graph here that maybe you'll recognize from lecture, just kind of a runtime graph. So if we have our g of n function, maybe that's somewhere like this. It is growing really, really fast because it is a worst case runtime of n to the 9th power. Actually, no, that is its best case runtime. G of n is greater than or equal to n to the 9th for all of its outputs. So at best, it's n to the 9th, and at worst, it could be something way bigger than that, like n to the 10th or n to the 100th or something like that. Anyways, so that is g of n, and we have Jane's algorithm, and we know that it is big O of g of n. So basically, Jane's algorithm is going to be the same or better than g of n. So in this case, it's going to be below it visually on the graph. So if we make this in blue, Jane's algorithm is going to be somewhere down here. It's going to be underneath this big curve of n to the 9th power. But that's a problem for us. Actually, maybe it's a good thing for Jane because this is a lot of ambiguity that we have now. If we could maybe say that if we have constant time here, O of no, sorry, not O of n, O of 1 right here, that is a perfectly acceptable solution for what Jane's algorithm could be. And that fits within the parameters of what Mango Enterprises wants. They want algorithms that are n squared or better. So because we have all this ambiguity, we have all of these potential runtimes that Jane's algorithm could be, we cannot say that we should discard Jane's algorithm. Bob is wrong here. So let's kind of, let's see what I wrote down here for the solution, just kind of the same thing. Let me select all that bit better. There we go. No, we can't say that we can discard Jane's algorithm, since all we know is that Jane's algorithm's worst case runtime is O of n to the 9th power. In reality, it could be much better because it could be anything underneath that red curve there. Part C, final part. Bob analyzed Elizabeth's algorithm and proved that T sub e is big omega of g of n for some positive function g of n such that it is greater than or equal to this big algorithm there for all n is greater than or equal to 2. Assuming that Bob's proof is correct, show that Elizabeth's algorithm is also big omega of n cubed. So this is just a matter of figuring out what g of n's runtime is. So let's observe it. This is just a matter of picking at the dominant term here. So how we do this is we look at, first we look at each term individually. So we've got these 3 terms here. First off, we've got that n term at the front. That doesn't have any constants or anything surrounding it, so we just kind of rewrite it. So g of n is greater than or equal to n. Moving on to the second one, we've got this big constant out front, the 2 to the power of negative 251. That is a very, 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 very tiny number, but it is still a number nonetheless. It's not a variable. So we can disregard it and just look at that n cubed that's attached to it. So n plus n cubed. Now we've got that last term there. Same philosophy. 2 to the 251st power is monstrously big, but it's still just a constant, so we ignore it. So we just keep that n squared there, so n plus n cubed minus n squared. We look at the biggest term here, which is the n cubed in the middle, and that is going to be g of n's worst case runtime. So g of n is at worst, actually no, at best, since it's a greater than or equal to sign, it is at best, which is big omega of n cubed. So that's what we can say about g of n. So how can we relate that to Elizabeth's algorithm, T sub e of n? So it looks like it's saying here that Elizabeth's algorithm is at best matching. No, how do I say that? Yeah, it's at best matching g of n's runtime. And since we said that g of n's runtime is n cubed, we can say that Elizabeth's runtime is at best n cubed. So there we go. That's exactly what they wanted us to show here. They wanted us to show that Elizabeth's algorithm is at best n cubed, and we showed that by saying that g of n's runtime is n cubed, and since Elizabeth's algorithm is at best g of n, that means that Elizabeth's algorithm is at best n cubed. There you go. Question 4, let S be an empty stack. Awesome, we're getting to these questions. Consider a sequence of intermixed push and pop calls on S. The arguments for the push calls are the numbers 1, 2, 3, 4, 5, and 6, one at a time in that order. So you can't do 2 before 1, for example. The pop calls happen at an arbitrary time, and each pop prints out the returned value. So keep in mind before we go into these parts how stacks work. Remember how you just keep adding items on top of the stack, and whenever you pop from the stack, it always removes it from the top of the stack. So let's say you push 1, 2, 3, 4, 5, and 6 onto the stack in that order. That means a 1 would be at the very bottom and 6 would be at the very top. And if you were to pop after that, it would return 6 first, and 6 would be removed from the stack. So if you were to do 6 push calls, so if you were to push 1, then push 2, all the way to push 6, and then 6 pop calls, it would return 6, 5, 4, 3, 2, 1. So that's just a brief rundown of how stacks work. And now we can go and get into these subparts. So starting with A, is the printed sequence 4, 3, 5, 6, 2, 1 possible? Explain your answer. So let's start by going through this. The first number that we need to pop is 4. So let's kind of build up our stack until we hit 4. So let's start with our empty stack, and then we'll go ahead and push the numbers onto it. We can only go in the order of 1 increasing, so we first have to push 1 onto it, then we push 2, then push 3, and then push 4. So now our stack looks like this. We've got 1 at the very bottom, followed by 2, 3, and then 4 at the very top. Now we need to have 4 printed out now. We need to have 4 as our first element that is popped. So now you can go ahead and execute one pop call to go ahead and print that into our desired output here. So we go ahead and pop 4 from the top. It is removed and it is returned. So now we need to go ahead and pop 3. So we need to have 3 printed next. Fortunately, 3 is already the next item at the very top of the stack, so you can just go ahead and do another pop already. So you can go ahead and pop 3 from the top, and it is removed and returned. Now the next thing we need to remove is 5, and it unfortunately isn't in the stack yet, so we need to go ahead and push items into it until we hit 5. So since we've already pushed items 1 through 4, the next item that we push is 5. So we go ahead and push item 5 onto the stack, and hey, that is actually the next number that we need to return here. So let's go ahead and do a pop. It is removed from the stack and it is returned. So now we've got 4 pushed, then 3, then 5. Or sorry, push was the wrong word there. We have popped 4, then 3, then 5 so far. And now we need to go ahead and pop 6. Again, just like 5, 6 is not in the stack already, so we need to go ahead and push items until we hit it. So the next number that we push here is 6, since we've already pushed 1 through 5. So we go ahead and push 6. It is now at the top of the stack, so we go ahead and pop it, since it's the next item that we need. So 4, 3, 5, 6. And now we just need a 2 and then 1. Unfortunately, if we just do 2 more pops after this, we will get those. So we go ahead and pop, we return 2, pop again, and we get 1, and we now have our empty stack. And hey, if you look at all of the red circled numbers there, it is the exact sequence that we needed, 4, 3, 5, 6, 2, 1. So we can say that yes, we can print the sequence 4, 3, 5, 6, 2, 1 here. Part B, is the printed sequence 5, 6, 3, 4, 2, 1 possible? Explain. So let's kind of go through the same logic that we did previously. So the first number that we need to print is 5. So let's kind of build up our stack until we hit 5 at the very top. So we have our empty stack. Let's go ahead and push 1, then push 2, then 3, then 4, then 5. Cool, we've got 5 at the top of the stack. Let's go ahead and do a pop. So that pop will return 5 and remove it from the top of the stack, and we successfully have 5 as the first printed value. So now we need 6. So let's go ahead and push items until we have 6 at the top of the stack. So let's go ahead and push 6 onto it, and there we go. We have 6 at the very top. Let's do a pop to remove it and return it. So now we've got 5 and then 6 printed, but we've got a problem. We need to return 3 next, but we can't really push anymore. We can only pop at this point, and the next pop, if we were to do a pop at this point, we would return 4, since 4 is at the very top of the stack. We've got a problem, so we can't pop 3 next, so unfortunately, the sequence of 5, 6, 3, 4, 2, 1 is not possible here. Question 5, this is a Q question. Let Q be an empty... Wow, they used the letter Q to represent a Q. That's insane. Let it be an empty Q implemented using a circular array of capacity 4. The Q starts with a front indice and a back indice. We run the following sequence of operations on the Q. So knowing all of that, let's do these 2 parts here. So starting with A, show the content of the array and the location of indices F and B after running the sequence. So basically just write this all out vertically, visually, and then that is the answer. So let's go ahead and do this. So we have a circular array of size 4, so let's write that out as a big rectangle. It has 4 elements in it, and we have a front and a back index. So they start at index 0 of the array, which is the very front. So F and B are both going to be right there at the very start. So now that we have all of this, let's go ahead and run all of these calls. So first off, we have an on queue of A. So how on queues work in a queue is you add it to the very start, wherever the front index is. So let's put A right where F is, right at the very start. So we put A right there, and we're going to move the front index over 1 unit. We're going to move F to right there at index 1. Okay, so that is on queue A all done. Now let's do on queue B. Same logic, we put the element we're inserting right at the front index. So let's put B right there, and then move F forward 1 index. So now we've on queued B. Now we need to on queue C, same thing. We put the C right where the front index is, and then move it forward 1 cell. So that is on queue C all done. And now we have to dequeue. So how dequeues work in queues is you remove the oldest element in the queue. So it's the opposite of how stacks work. Stacks, whenever you pop from the stack, you remove the very top element, the latest element added. But here we need to remove the oldest. So we look at where the back index is and remove that element. In this case, it's A. So we erase A and then move the back index forward 1 element. So there we go. We successfully dequeued. Now we have more practice with that. We have to do another dequeue. So we look at where the index or the back index is and remove that element. So we erase B and then move forward the back index 1 step. So that is a dequeue call. Now we've got a couple more of each. So we have an on queue here. We've got an on queue D. So we put a D right where the front index is and then move it forward 1. Since this is a circular array, this front index is going to wrap around all the way to the very start. So that is an on queue D. Now we need to on queue E, exact same thing. Put an E where the front index is, then move it forward 1. So there we go, on queue E. Now we need to do a dequeue. So again, we just erase the element where the back index is. So in this case, we erase C and then move the back index forward 1 cell. And now we just need to on queue F. So we put in F right where the front index is and move it forward 1. And that is the full representation of the final queue. Part B, can we change the order of the 3 dequeue calls such that the front index is 2 and the back index is 0 after finishing the sequence of operations? No, we can't, because no matter in what order we have the on queue and dequeue calls, they're always going to move the front and back indices forward 1 cell each every time, no more, no less. And since we have, I should actually kind of erase all this stuff. Since we have 6 on queue calls and 3 dequeue calls, that means every single time, no matter how we order all of these on queue and dequeue calls, the front index is always going to move forward 6 elements, and the back index is always going to move forward 3 elements. So no matter how we order this, the front and back indices are always going to be planted right there at the end of all the calls. So because of that, no, we cannot make those indices appear in any different locations, such as f equals 2 and b equals 0. And that's basically what I wrote down here. Let's bring that up. No, because only 3 dequeue calls are made. Both f and b must move forward 3 indices, and they can't land on 2 and 0 respectively. Question 6, we're still on queues. So we've got a queue, and we consider a sequence of intermixed on-queue and dequeue calls on the queue. The arguments for the on-queue calls are the numbers 1, 2, 3, 4, 5, and 6, one at a time in that order. The dequeue calls can happen whenever, and each dequeue prints out the return value. We've only got one part for this question. Is the printed sequence 1, 2, 3, 4, 6, 5 possible? So this is kind of a retread of the stacks question that we had earlier. So first, let's get a refresher on what queues mean again. Queues, how they operate is you keep adding to the front of the queue. You keep adding elements to filling up the queue, but whenever you pop from the queue, whenever you dequeue it, it returns the oldest element in the queue. So for example, if we have maybe a queue that looks like this, and we on queue A, then B, then C, then D, whenever we do an on queue, instead of behaving like a stack where we erase the newest element in the stack, we are actually going to erase the oldest element. So we're going to dequeue A from all of this. By the way, whenever I say dequeue, I think of Dairy Queen. I'm a fat ass. But anyways, All right, so can we return this printed sequence of 1, 2, 3, 4, 6, 5, given all of these restraints? We can only on-cue the numbers 1 through 6 in that order, so can we return something that's very similar to it, but with a swapped 5 and 6? And the answer is no, because you can't on-cue elements out of order in this case because of these restrictions. Since we on-cue the numbers 1 through 6 in that order, whenever we dequeue, it also has to be in that order. It has to dequeue 1, then 2, then 3, then 4, then 5, then 6. We can't do that out of order, and switching up whenever we make those dequeue calls isn't going to change that. For example, if we on-cue 1, then 2, then 3, then do a dequeue, that's going to return 1. And if we do the exact same thing, if we do 1, then 2, then 3, then 4, then 5, then 6, and then do a dequeue, it's still just going to return 1. So no matter how we kind of mix up these on-cue and dequeue calls, it's still just going to return the exact list that we have up here, 1 through 6. And because it wants a sequence that is 1 through 4, then 6, then 5, that isn't possible. So unfortunately, we can't return that. That's kind of what I've written down here. No, you can't queue elements out of order, and you can't dequeue elements out of order. Question 7, we have to draw the expression tree for this expression. So we've got, I'm not even going to say all of that. It's a lot of stuff going on. But how you draw these expression trees? So first off, it's a tree. It's got nodes. In this case, for expression trees, they only have a maximum of 2 leaves coming off of each node. So we've got nodes and the leaves coming off of it, and then, they can kind of keep going further like that, having more and more layers. And yeah, that's what trees are. But how we set this up is the problem. So first, how we do these is we look at the latest expression, or the latest operation that we do on this expression. And in this case, it's going to be this division symbol in the middle. So we're going to have to figure out what this big sub-expression is on the left. Same with this one on the right. We need to figure out what by plus c is, and then we divide the two. We divide the left by the right, and that is the final operation that you do on this big expression. So because of that, since it's the last one, we are going to put that at the very top. Let's put that division symbol right there in a big node and have it be the big king of all of this. So we're going to have 2 leaves coming off of it. They're going to have some expressions coming off of it. And what those are the final expressions for the 2 sub-expressions that we just talked about. So now we just kind of recurse and we do the same thing, but for each of these 2 sub-expressions. So let's start off with the left one. So let's do the final operation of the expression bx squared minus axy. In this case, it's going to be the subtraction symbol. So we first find out what bx squared is, and then find out what axy is, and then we subtract the 2. So that's the last one that we do there, so let's put the minus sign right there. So now we've got that, and we recurse again. We've got the left here, the bx squared, and the right here, the axy, and we need to recurse again. We need to figure out the final expression from both, the final operation from both of these. So let's do the left one first. Again, that's kind of how I like doing it. We've got bx squared there. This really has, it looks like the final operation is going to be a multiplication here. First, you have to figure out what x squared is, and then finally, you need to do b times x squared. So we're going to put a multiplication symbol right there, or really an asterisk. Then we've got the 2 leaves there, and the 2 things being multiplied are b and x squared. So that is our new sub-expressions. I like doing the left one first. Let's go ahead and do that. And you'll notice that we now have just a standalone element. It's just b. There's no operations going on in there. So we can finally cap off this big leaf trace that we've done and just put a b here on the very left. And now we're done with all of that. So now we can kind of go back up the tree and fill in all of these missing leaves that we've now created. So let's go ahead and go back to here. We've got b times something. What we were doing there is figuring out what this is. It's b times x squared. So now let's go ahead and do the sub-expression tree for x squared. So that is just x squared, which is just x times x. So we're going to have an asterisk here, and then it's x times x, so it's x times x. So that is the sub-expression tree there. You'll notice how we can kind of see this now visually. So we've got b times x times x. That's how you can kind of read all of this. So that's how expression trees work. We've now filled out all of this, so now we can go back up here and figure out what we're doing here. So this minus symbol was all of this here. We were figuring out minus axy. So now let's go ahead and figure out that sub-expression there. So let's do that. So this is just 3 multiplications in a row. Properties of multiplication tell you that it doesn't really matter what order you do it all in. So we just have a times symbol there, and then we still only have 2 leaves coming off of it, but it doesn't really matter if we do a and then another multiplication symbol, or multiplication symbol and then y. So let's just do a and then multiplication, and then after that we've got x and then y, so let's write x and then y. So let's write that a little bigger so it's easier. We got x and then y. Awesome. That is actually a really shitty a. Let me fix that. Awesome. So there we go. That is the expression tree for this term here, the bx squared minus axy that we've now filled out. I hope we have enough room for the rightmost half. I kind of used up a lot for the left, but I think we'll be fine. Now we just have to do the expression tree for by plus c. This is a lot easier. So it looks like the final expression that we do here is the plus in the middle. So let's put a plus right there. 2 things coming off of it are the by and the c. So let's go ahead and do the by first. The final operation that we do there is multiplication. So put a multiplication right there. And the 2 terms coming off of it, well, that's just going to be b and y. So it's b and y. We filled that out. Finally, we just have the remainder of whatever this plus was, which is the c. And we are all done. That is the full expression tree for our expression here. Part B, right, the pre-order, in-order, post-order, and level traversals of the tree from, I don't know why they wrote B, this is part A, but whatever. We need to write all of this, so let's do that. So let's go through each of these one by one. So let's start with pre-order. So let's write pre-order. Cool. So how pre-order traversals work is first you evaluate the center node, then you do the left node, and then the right node. So in this case, we're going to start with the very top, and we will look at the center node first. So we're going to write out the center, which is the division. Then we go to the left, and we kind of recurse like that. So we do the NLR all over again. So we do the center node, which is minus, and then we go left. So then we do the times, and then we do b. And now we kind of go up, and we realize, okay, after we kind of go left, then we need to go right. So we go right here, and then we do the whole thing again. We write the center node, which is the multiplying there, and then we go left, which is the x. So that is that all done, and then we go up and then right again and do the other x. So that is all done. So now we kind of go back up like that, and we go right. So then we go right, and we do the center node there, which is multiplication. Then we go left, a, then we go right, which is the center. So we do the multiplication, then left, the x, then right, the y. Then we go all the way back up, and we do a right. So then the right there is the plus, then left, the center there is a multiplication. Then left, it's a b, then we go up and then down to the right, that's a y, then all the way up, and then back down to the c is c. And that is the full pre-order traversal. It's NLR. That's the shorthand of remembering how you do this. So now we're going to go on to the in-order traversal. How this works is, I have it written off to the side here, it's LNR. So now instead of, oh God, how am I going to erase all of this? Like this. Yeah, you just erase it. Ooh. There we go. Okay. In order traversal, it goes left, then center, then right. So in this case, before we write out the center node there, we're going to go all the way down to the left and then write B before we do anything. So let's write B, and then we go up one and then do the center node there, since that's the next step. The second step there is writing out the center node, so we do B and then star, and then we go off to the right and do the whole thing over again. So then we go to the left, we write X, then we go back up to the center, which is star, and then we go down to the right, that's X, then we go all the way back up here and go there. So now we've got that there, we're going to need to do a minus, then we go down all the way to the left, we do A, back up here, we do multiplication, down all the way to the left, we do X, up to the center, we do multiplication, down to the right, we do Y, going all the way back up here, we can finally do the center of this whole tree here, which is the division. Then we go down all the way to the left, we do B, then up to the center, we do multiplication, down to the right, we do Y, all the way back up to the center here, we do plus, and then finally down to the right, we do C. So that is in-order traversal. Now we need to do post-order traversal. So post-order, how this works is LRN. So we do the center node at the very last in this case. So first, I need to erase everything, which takes a long time. I apologize. I need to figure out a more efficient way to do this. Okay, that looks good to me. So post order is left, then right, then center. So how we do this is we go all the way down to the left, and we put a B right there, so B. So we need to go back up, but then we go all the way back down again to the right, since that's the next thing that we do. We go all the way down to the left, then all the way down to the right, and then finally do the center node. So it goes down to the left, then down to the right, which involves going down to the left again. So then we do X. Then we go back up, down back to the right, do the X. Then we go up and finally do that center node, the multiplication right there. We do the same thing, go back to the center, multiplication, go back up, and then all the way back down to the left. We'd have an A there. We go back up, then down to the left, that's an X. Up, down to the right, we have a Y. Up to the center, multiplication, up to the center, multiplication, up to the center, subtraction, going back up, then all the way down to the left, we have B, up, down to the right, we have Y, up to the center, we have multiplication, up, down to the right, we have C, up to the center, we have plus, and up to the center, we finally have that division. Finally, we have level traversal. This is the easiest in my opinion, but this is the one traversal here that I got wrong when I took this, because it's different from all the others. I'll explain what I mean in 5 seconds. There we go. Level traversal isn't some kind of funky traversal like this, where it's like left, then center, then right, or something else like that. You literally just read it like a book. So first we're going to do the division, since it's at the very top, and then we're going to do subtraction, then addition, because those are the next two lines that we have here. And that's all you do. You just kind of go line by line. And it's helpful to have your tree written out like this in a neat way, so that's easy to tell what each of the levels are in your tree. So let's go ahead and keep on doing this. We've got multiplication, then multiplication, then multiplication, then C. Then we've got B, multiplication, A, multiplication, B, then Y. Then we've got X, then X, then X, then Y. And that is all of the level traversals of the expression tree. Question 8, the last one, you've made it. Dan and Aaron are discussing the behavior of the recursive algorithm below. So let's just analyze this and soak it up a little bit before you dive into the questions. So we have a function foo here, and it looks like it's a recursive function. So we've got a base case right at the top. When n equals 1, then just return. Then we have, let me encompass that a little better. There we go. Then we've got a for loop inside of it. So for I equals 1, for I all the way until n, you're going to run bar. So basically, for whatever value of n, for whatever value of n you put into this, bar is going to run n times. So that's what that means. And then at the very end, it's going to return n plus foo of b of n. And this b of n is actually integral to what a and b are talking about, but we'll just keep it as that for now. So it's going to call b of n again, and then foo is going to run again, and it's going to recurse, and it's going to do a bunch more of these foo calls, because that's how recursive functions work. So let's go ahead and start with part A. So Dan says if b of n equals n minus 1, then the number of times foo calls bar is O of n. Is Dan right? So let's kind of rewrite this this b of n as n minus 1, so we can kind of get a feel for what this function is doing. So we've got this function foo, which has n as an argument. And inside of it, it's going to run, again, when we said earlier, it's going to run bar n times. Since that's what this for loop is doing, I is going to run all the way until n, and bar is going to run n times. After all of that, it's going to call foo and run it n minus 1, or it's going to call foo with an argument of n minus 1. So what this is going to do is, if you plug in foo of n, it's going to run bar n times, and then call foo of n minus 1. So this is going to get big fast because there's a lot of foo calls here, and you're only subtracting 1 from n every time. So upon the first call of foo, if we do foo of n, bar is going to be called n times. So we're going to write n right here. Following that, we're going to call foo of n minus 1. So that means bar is going to be called n minus 1 times, since that's what we specified in the argument. Now, if we do another call of foo, that's going to be n minus 2, since it's n minus 1 minus 1. So after we do that, we go back up to the top. Bar is going to be called n minus 2 times. And maybe you can kind of get an idea of how this is going to keep going. We're going to keep subtracting 1 from n every time, sticking it back into the argument of foo, and calling bar that many times. So we're going to call bar n times, then n minus 1 times, then n minus 2 times, all the way down until our base case, when n equals 1, and in which case the function halts, and bar is called just a single time. So that is what this function is doing. Now we need to figure out what the runtime of this bad boy is here. If maybe you can recognize that. I can't quite remember if you're supposed to remember this at this point in the course, but this is n squared. What this is a summation, and this is represented by n times n minus 1 all over 2. And if you multiply it out, we get n squared minus n all over 2, and we have n squared as the dominant term here. So in this case, its runtime is O of n squared. That isn't what Dan said, so he is wrong. No. Part B, Aaron says that if b of n equals n over 2, then the number of times foo calls bar is O of n. Is Aaron right? So this is kind of just doing what we did back up here, but instead of having n minus 1 for b of n, we have n over 2 for b of n. So let's go ahead and rewrite all of this like that, since it's just the same work but with different numbers. Erase all of this. Cool. Now we have, instead of n minus 1, we've got n divided by 2. Cool. So let's kind of go over what this function is doing again. For any call of foo with a value of n in it, bar is going to first run n times. And then foo is called again, but this time the argument is n divided by 2. So upon the next call of foo, bar is going to be run n over 2 times. And then when we do this foo call again, it's going to be n over 2, which is n over 4. So upon the next call of foo, bar is going to be called n over 4 times. And then on the next call, we do n over 4 over 2, which is n over 8. So that means bar is called n over 8 times. And you can kind of see how this is going to go. It's going to be n over 2 plus n over 4 plus over 8 plus over 16 over 32, 64. Got to keep going on like that all the way down to the base case, which is 1. Or at least close to the base case. I think So I think in these cases they specify that n is a power of 2, but that's getting technical. Anyways, so how do we express this as a runtime? Well, think of it as like, we can actually do this kind of visually, like with geometry. So if we have a square here, let's say this square represents n, let's add on to it n squared, or sorry, n over 2. So that's just going to be exactly half the size of this square. So let's kind of make a rectangle that is half the size of that. It's n over 2. Now we've got n over 4, which is half the size of that rectangle. So we've got this right there, which is n over 4. Then we've got n over 8, which is half the size of that, n over 8. Then n over 16, which is half the size of that. You can see how this is going to keep going. It's going to keep filling in smaller and smaller pieces of this down to infinity until eventually we kind of basically fill this whole thing in, which is 2n. We're approaching 2n here. And this is linear. O of 2n is just O of n. So, yeah, Aaron is right. This whole function is O of n. Awesome. I wrote yen there because I'm thinking of Aaron and yes at the same time. I'm hungry.